Welcome back to 3120. We're going to continue our discussion on stereoselective reduction of aldehydes and ketones. And today's lecture 29. And we just finished this stuff here, StereoChem Newman projections. So we're going to focus on the effect of electronic substituents and the chelation effect. So let's call this the effect of electronic substituents on, let's call this the Felkin Ahn model. So recall last time there was this model where we could use a Newman projection to orient which side the nucleophile attacks. All right, so let's jump right into it. So this will be, let's take a look at an example here. And this will be sort of a larger molecule compared to what we've been drawing before. All right, so we have an aldehyde, and we're going to treat this with an enolate. Okay, so there's your nucleophilic carbon. Where did this enolate come from? Well, you can imagine you would have like a methyl ester like this, treat that with LDA, and then you can generate your enolate. And so this enolate is going to come down and it's going to attack here, but we need to understand what the Newman projection looks like so we know what stereochemical product we're going to get. So let's apply the same rules and principles to what we had last time. So let's take our eye and let's look right through this bond right here. So I'm going to do that, and I'm just going to flip this whole structure because I like having the carbonyl on top, but you don't have to do that. And if we look across and through this bond, there's a number of different things that you can see. So you can see that this whole big group here is right behind this oxygen carbonyl. So that's going to look like this carbon with a methyl group, and then this phenyl group. And then what you're going to have is this nitrogen like this, and then you're going to have the hydrogen. Yeah, that's a hydrogen, by the way, right here. Not a methyl group, hydrogen. So your hydrogen will be here. Okay. So based on what we've learned, which one is the bigger group, right? And it's not necessarily the overall size, but it's the largest group that is actually closest to the carbonyl. So if you actually go here you have a nitrogen with, CH2, CH2. Here you have a carbon with a CH3, then a CH2, okay? So it seems like these ones are perhaps fairly similar, but let's definitely put the this group as a bigger group, okay? And if we do that, we're going to generate an energy conformer that looks like this. And the other low energy conformer will look like a carbon chain, hydrogen, will look something like this. Okay, so two low energy conformers, and then if you think of your enolate, all right, so your enolate could attack here, or it could attack here, or it could attack here, or it could attack here. The path of least resistance is going to be right here where the proton is. So you can imagine if you have your lithium enolate, this will come down, this will attack like I'm showing you right there. So what does that look like? So if you do that, this will look like put our OH there. So let's just put the stuff on the back, everything 180 degrees away from each other. And then this thing just attacked. And that's going to look like, that was the enolate that attacked. So here's your new, that's your new carbon-carbon bond. Okay, so that attacked. Okay, so if we actually translate this to something that's either syn or anti, first we need to see whether the carbon chain, the longest carbon chain, is in the plane of the page. If we actually do that, you can see we start with phenyl, carbon, 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 carbon. So our longest carbon chain is in the plane of the page. And what you have over here are two groups that are on the same side, that are syn to each other. So in terms of drawing out what the product will look like, this corresponds to a syn product. And that might look something like this. Where you have now your you have your hydroxyl group. Or you have your hydroxyl group and the NH group on the same side. As I'm showing you here. So here's our hydroxyl group and this N group, they're on the same side. So this corresponds to the syn product, okay? So that's what we are predicting. That will be the major product. However, if you actually do this reaction, as I'm showing you up here, you're actually going to generate the anti-product as the major product. And the anti-product is going to look like this. There's your anti-product. So you can see that the OH and this group are opposite from one another. That's a stereoisomer of this one. So if you do this experimentally, this is your anti-product. And furthermore, this anti-product is formed in a 20-to-1 ratio. Previously, we've seen 3-to-1 ratios, but this one is even more stereospecific, 20-to-1. Very little minor syn product is formed. So there's something definitely wrong with our model here. Even though we did put what we thought was the largest substituent 90 degrees, we ignored one important fact. The thing that we need to consider is that this nitrogen here actually has lone pair of electrons. And if we actually use this model here as the path of least resistance, one of the problems is that you have these nitrogen lone pairs here you have these oxygen lone pairs, you're going to get a lot of electronic repulsion. This is actually not a low energy conformer. So what we need to do is we need to revise what our low energy conformer looks like, given the fact that we have electronic substituents. So if this is causing undue stress to the molecule, then it makes sense to put those electronic substituents, side chains, the nitrogen has lone pairs, let's now put that 90 degrees away. So let's see what that is going to look like. So let's put electronic substituent 90 degrees away from the carbonyl. All right, so let's take a look at the Felkin Ahn model. So what we should do actually is draw that one up there, okay? This one right here, we're going to rotate it a little bit so that this nitrogen is now 90 degrees away. And if we do that, that's going to shift things around a little bit. Now our low energy conformer is going to look like this. So you can see the rotation from there, brought that nitrogen, which used to be up here, brought this down to here. And by doing so, what we've done is we've now changed the site of attack for that enolate. So this is now the low energy conformer. So if we now take that lithium enolate, it's going to attack the path of least resistance, which is right here, at 107 degrees through that Bürgi-Dunitz angle, like we talked about last lecture. So when we do that, let's see what this looks like. And I'm worried I'm going to run out of space, so maybe what I'll do, well, let's see how this works. So if we do that, just because our law of substituents here, this OH is going to go up there. Carbon methanol groups there. You're going to have your, everything's going to be, 180 degrees from each other, and it's going to be staggered, so 60 degrees from each other. And it's going to look like this after the reaction. Okay, so how do we draw this out? And what do we need to do? We need to put the longest carbon chain in the plane of the page. So has that been done? No. You can see the longest carbon chain is here, but then it goes into this ester here. So we need to rotate this in such a way that we put those groups in the longest plane of the page. So what we can do is let's take this here and rotate 120 degrees to put longest carbon chain in the plane of the page. So I'm going to draw that, skip over this right over here, and draw what this rotation looks like right here. So that's going to look like so now you can see that we have the longest carbon chain in the plane of the page as I'm circling here. So now we're in good shape. But more importantly, you can see that this group here with the nitrogen with the two benzyl groups and then this hydroxyl group, they're on opposite sides. So this corresponds to the anti. And therefore, this rationalizes why, when we draw the product there, that's the anti-product. All right, so there are some very interesting and important lessons that we've learned here. So let's revise our Felkin Ahn model. We said that we should put the largest substituent 90 degrees from the carbonyl group, but if we have a group that has electronics or an electronegative substituent, then we need to put that 90 degrees away. So here's our Felkin Ahn model, our revised Felkin Ahn model. So first thing you should always do is draw a Newman projection. Now, let's talk about electronic substitution. So if X is like an electronegative substituent, so this could be something like OR, or if X is equal to like NR2, like we just saw over there, or even things like thiols. These have lone pair of electrons, so these are good electronic or electronegative substituents. So the first thing you should do, therefore, is put the electronegative (90 degrees) to the carbonyl. Okay? If you don't have an electronegative substituent, then you default to what we learned last time, was putting the largest group 90 degrees. If no electronegative substituent, put the largest group (90 degrees) to the carbonyl. Step 4, attack 170 degrees along that Berge-Dunix angle with a nucleophile. Uh, 170 degrees along Berge-Dunix angle along the path of least resistance. Step 5, flatten the Newman projection. And orient the longest carbon chain in the plane of the page. And then step 6 will, of course, be assign syn or anti based on those substituents relative to one another. All right, good stuff. All right, so write that down. I'm going to use that whiteboard in just a second. And we're going to look at chelation in just a second. All right, so there will be a title, but for now, I won't put a title down. All right, so here is an example where we take this ketone and treat this with sodium borohydride and methanol. And then my question for you is, what is this going to look like? All right, so we've learned some important things already. So if we take our eye, and if we look along this carbon-carbon bond, let's draw a Newman projection. We know that the sulfur has electrons there. So we know to put that 90 degrees from the carbonyl. So let's exactly do that. So here we can have our thiol-methyl group, and then we can have our alkyl chain up here, and then we'll have our phenyl, then we'll have our hydrogen group. Okay, so don't forget there's a hydrogen there. So that's one of the low energy conformers. If you rotate that 180 degrees, your other low energy conformer will have the thiol-methyl group over here. Everything's rotated, and it would look like this. Two different groups. And you can see that the path of least resistance on this molecule here will be right here. Or sorry, right here. Okay, so you can imagine your borohydride. This will come, this will attack right here. Right, this one's a little too sterically hindered. This one you have an alkyl chain. So this is the path of least resistance. So let's see what that looks like. Okay, so you can see we have, we're lucky we have our longest carbon chain in the plane of the page. So if we actually assign this, you can see that the OH group and the thiol-methyl group are on the same side, so that's called syn. So if we actually draw what the product will look like, it's going to look just like this. All right, so pretty straightforward, right? Now, it turns out if you actually do this reaction with a different hydride reagent, so if you actually do this reaction with the same substrate, but instead of using sodium borohydride, we're going to use something called zinc borohydride. And zinc is a divalent and a +2 charge. So you're going to have two borohydride units attached to it. So the same type of nucleophile is going to attack, but if you actually do this reaction, you actually observe the other stereoisomer. Which is the anti-product. And you might be puzzled because why would there be such a difference if you have the same nucleophile, you have the same molecule? One's giving you syn, zinc borohydride is giving you anti. So the title of this one is actually called Chelation and the Effect of Reversing Stereochemical Control. So the zinc is going to play an important part in this reaction. All right. So let's take a look and think about how this is actually going to happen. So I think what I'll do is I will erase this board up here. All right, let's get my chalk. And let's try to think about how zinc changes the stereochemical outcome of that reaction. So what we need to do is look at the Felkin Ahn model, or look at the Newman projection that we were using initially to attack the borohydride. So I'm just recopying this one right here. And clearly, sodium borohydride is not, well, zinc borohydride is not reacting this way because we get the other stereoisomer. So let's think about zinc for a second. Zinc, as a divalent metal ion, very much attracted to electrons. And if we place zinc in solution here, it's going to be very much attracted to both of these. The problem is these are a little too far apart. So in order for the zinc to take advantage of both sets of electrons, this thiol group is going to come up closer so that you can form this complex. So in other words, it's actually going to be eclipsing. You're going to have your zinc 2+ right here. There's the ionic compound, the ionic contacts. Here's your thiomethyl. And you can see that's almost eclipsing just due to that zinc. So the zinc prevents and avoids those electronic repulsion because it essentially neutralizes it. So if you do that, you can see here that you change the Newman projection considerably. Right now you have the path of least resistance on the other side. So if we take our sodium borohydride, our zinc borohydride. The zinc borohydride, this is going to attack 109 degrees, 107 degrees. What that's going to look like. You're going to get something that looks like this. All right? Now, before you jump to conclusions and say, oh, wait, look, it's still sin, don't forget what you need to do. Follow your checklist, right? So you attack 107 degrees along the Berge-Dunitz angle, and then you've got to flatten the Newman projection, orient the longest carbon chain in the plane of the page. So we don't have the longest carbon chain in the plane of the page, as you can see. So we need to do a rotation. And essentially what we're going to do is, well, there's different ways you could do it, but let's just rotate this up. And if we do that and put that on top, it's going to look like this. And you can see here, now you have the longest carbon chain in the plane of the page, and then these two groups here are anti to each other, which takes into account the final product that we get, which is anti. So zinc has something known as a chelation character, and essentially chelation involves coordination of the two heteroatoms carrying the lone pair electrons to the same metal atom. In this case, as we can see, the zinc is attracted to both oxygen and the sulfur. All right, so let's take a look at some good examples of metals that could be good chelators. So these are typically divalent metal ions. Sometimes trivalent work well, but monovalent ions like sodium, potassium, lithium typically do not work so well. All right, metals typically involved in chelation. So if you're doing like a stereochemical reduction or something, metals commonly used. So things like magnesium 2+, zinc 2+, we just saw that example, copper 2+, titanium 4+, cerium 3+, manganese 2+. So these are typically used in chelation. Metals that are usually not involved are monovalent ions, typically like lithium, potassium, and sodium. Okay, and then just to emphasize and recap, here's your Felkin Ahn model. You have some heteroatom X, and then your metal essentially will bring these in close proximity to each other. We'll just put metal, I'll just say 2+. And you get those strong ionic contacts. And what that will do is that will change the orientation of attack of the Newman projection. All right, good stuff. All right, so let's take a look at, so why don't we just sort of summarize and talk about some of the criteria for determining stereoselectivity. All right, so I think I'll do that right here. So as you can see, there's a number of factors, right? We got to consider the size of the group. We have to consider whether there's an electronegative element, like oxygen, sulfur, or nitrogen. And then we also have to consider what kind of metal we're using. So I have like a little flow chart here that it will be quite useful when you are working on problems. And let's just look at a classic example where you have X, Y, and Z. All right, so the first question you want to ask is there a heteroatom at position X, Y, and Z? So there's two possible answers, yes or no. If the answer is no, then what you're going to do is you're going to use the Felkin Ahn model guidelines that I just erased, and you're going to orient the largest group perpendicular to the carbonyl. Okay, so that's going to look like this. We've seen this already. Large group here, medium up there, and then small. Okay, question though is that if there is, then you're going to have to ask yourself another question. So if there is a heteroatom with a chiral carbon, if your answer is yes, what's the next question you should be asking? All right, and we just talked about chelation. So is there a metal capable of chelation? So if there isn't a metal, then you're going to use the Felkin Ahn model, except you're going to put the electronegative heteroatom perpendicular to the carbonyl. Okay, so this would look something like this, okay? X is your heteroatom. X has lone electrons. So you want to keep that far away, 90 degrees from the carbonyl group. So you can sort of anticipate, though, this flow chart here. If the answer is yes, right? If you do have one of those di or trivalent metals, or even titanium 4+, then you got to use the chelation model. And you want to hold the metal ion close to the carbonyl group and the heteroatom. So your Felkin Ahn model will shift and it will look like this. Ionic contacts. Okay, so but this is sort of like one of those engineering like flowcharts, you know, you can think of like those COVID flowcharts, like are you sick? Do you have any of these symptoms? No, okay, then you can go on to the next step. If you answer yes, then it's going to say, okay, isolate and stay home. So for each of these, there's always a pathway to success, and definitely use this when you're approaching these types of problems. All right, so in summary, I just want to say just a couple brief things. So just remember, for these carbonyl compounds, nucleophiles can attack with a high degree of selectivity, stereospecificity, and you need to consider things like the bulkiness of the group, the electronics of the heteroatom, and furthermore, if there's any metals capable of chelating. So many different factors involved. All right, so that concludes our section on stereo-selective reduction of aldehydes and ketones. I hope you enjoyed that. And yeah, see you next time.